So, since a lot of people are asking how do I build a jet engine that does not explode itself immediately upon spooling up, I decided to look into this a little bit and actually wire up some logic that will keep the engine from blowing itself to pieces and allow you to control it a little bit. And this is what this is. Um, to start, our controls here are our engine toggle button to engage the engine or turn it off. We have a throttle that we have set so that it gives us the actual RPS that we want the engine to run at. And we have a little readout for the actual RPS that the engine is running at, as well as the temperature. So, what we need to do first, we have our toggle button here that when we press goes into this AND gate. Now, this AND gate basically requires both these inputs to be on in order to transmit a signal. In order for the other signal to turn on, we are using a threshold gate. This threshold gate is hooked up to the RPS output of our intake, and the threshold is set to -1 because sometimes turbines tend to like to run backwards for some reason, and 3. That is 3 RPS. Within this threshold gate will output a signal. So both from our button and from the threshold is now on. So what happens next? Well, the output goes into our jet compressor. This compressor has a small electric engine that will start to spool up the engine and make it actually go above the 0.6 RPS that it needs to ignite itself. Once, however, we have reached that ignition point, the engine needs some throttle as well as fuel to actually start. So to do so, we have to skip ahead a little bit and skip this logic here and look at this. This little switch box here, this is a numerical switch box. What this actually provides us with is in its off state, which is this line here, we're giving it a number. This number is 0.3. This is our starting throttle. This is the throttle that is used to get the engine, once it has the ignition point, once it has the fuel, to actually start spooling and continue to increase in RPS rather than shutting itself down again. In order to turn the fuel on, we have another threshold gate over here that runs between the low threshold of where the engine will ignite first and the upper threshold of just shy before it blows itself to pieces, which is 200 RPS. And this will cut the fuel off if it's either below or above these numbers. This will help get our engine safe and not blow itself to pieces as it reaches higher RPS. Now the next thing we need to do is once we have actually reached the a necessary amount of RPS to keep the engine running, we want to actually control that it stays there. And to do so, we need to reduce our throttle, because 0.3 is going to let it continue to rev up further and further until it blows itself to pieces. So what we need to do is we need to control the throttle very precisely so that it stays where it is, because you all know when you start these things, they tend to just rev and immediately blow themselves to pieces. Now, if you have a dynamic system, and that dynamic system needs a very fine control in order to stay where you want it to stay, what you normally use is a PID controller. Now, these PID controllers, they seem intimidating at first, but their system is actually relatively simple. They have a set point that you give it where you want the system to be, and then you have a process variable, something like, in this case, the RPS from our intake, and the system will calculate how much difference there basically is. How much is the difference between where you are and where you want to be? And this difference we can then use to input as a throttle, because the difference will tell us, okay, I'm at 10 RPS, I want to be at 50. What's the difference? How much more throttle do I have to give it to get there? So this is basically what we use our PID controller for. Now, this PID controller, once enabled, will output a number that goes into our numerical switch box, onto the on side. Now, this on side will then transmit, once given, into a little clamp. Now, why are we using a clamp here? Because the PID has no way of setting a max or a minimum output. So the PID will tell you you're at 10 RPS, you want to be at 50, well, the throttle you need for that is 40. However, we can't use that. That is way too much. The throttle input only goes from 0 to 1, and setting it to 1 gives us such a quick spool up on the engine that it's very likely that it may run itself to pieces before the PID controller can react and say, hey, wait, hold on a minute, not so fast. So we clamp our output from between 0.1 to 0.6. And this will only allow the throttle to deviate between 0.1 and 0.6. This will reduce the speed at which the engine spools up and allows it to stay between the lines, as it were, with much more accuracy and not blow itself to pieces immediately. So, what happens when we spool this up then? Well, we click our little button, our compressor starts running, and once it reaches the threshold that we initially set of the 3 RPS, the AND gate will shut itself off. Now, this output then is now off, so our compressor no longer runs, but there's more connected here. That what we skipped earlier. So this goes into a small delay, and then into a NOT gate. Now, a NOT gate reverses the input. So if we have an on signal going in, an off signal comes out, and vice versa. So when this AND gate turns itself off, this NOT gate turns itself on. And what happens? What's connected here? Our PID controller is enabled, and our numerical switch box is switched from our initial throttle into the PID controlled throttle. That means that now the PID is controlling the engine output rather than our initial throttle. And once that then goes through our little clamp and back into the throttle, we now have the engine controlled by the set point of the PID. And what's the set point of the PID connected to? Our throttle. This throttle is now set to a minimum value of 10, where your engine is going to be idling, and a max value that we can set somewhere beneath the fuel shutoff and beneath the RPS that the engine blows itself to pieces at. And with this throttle, we then control the RPS output that we want the engine to run at. So all connected like this, and I'll show the PID values as well, which is 1, 0, and 0. Once this is all done and connected like this, and I have a more compact version in the workshop for you that's linked below, we can then spawn this, walk over to it, and start it using our button. And you'll hear that the engine is now spooling up, and you can see that the RPS here is slowly increasing. Once we reach our ignition point, at which point it will then run up using its initial throttle from our number. Once it reaches the throttle that we have set as a minimum, which is 10, where it will then stay at. And we can now command it to go faster, at which point it will spool up to what we have set, or we can say we want less, and it will start to slow down again. This can't blow itself to pieces because of our threshold, so even if we were to throttle this all the way up, and it for some reason overruns, which it sometimes does as you can see, the fuel shutoff will be hit, and there's no way this turbine can overrun itself into the 200 RPS or more, at which point it will blow itself to pieces. This will roughly hold the RPS at relatively constant amounts. The bouncing that you can see can be eliminated if you want to. You have to tweak the PID controller a little bit more, fiddle around with some clamps and so forth. But this works for the most part, and anything down the line that comes out of your turbine, which is this port, or of your exhaust, this little bounce does not really do much negative for you. There isn't really a difference that you can feel when you're flying with these things. But that's basically all the logic you need. And as I said, there is a more compact version on the workshop which has all this logic stuffed onto the side of one of these, which you can copy and place however many engines you want and connect them all up nicely. And that's basically all you need to know for these jet engines. That's how you get them to run safely, that's how you make sure that they don't blow up in your face, and how you get the most out of them.